Somewhere in a museum in Houston, Texas, there is a rock. It fits comfortably in the palm of a hand. It is dark and dense and unremarkable to look at, a piece of stone that most people would walk past without a second glance. But this particular rock traveled more than 2 billion kilometers to reach Earth. It was blasted off the surface of an asteroid by a collision of tremendous violence, flung into space, and drifted through the solar system for millions of years before Earth's gravity captured it. It fell through the atmosphere as a fireball, survived the burning descent, and landed somewhere on a field or a desert or a frozen plain. It is a piece of another world, a fragment of a world that formed 4.5 billion years ago and has never changed, never been melted, never been reshaped by the geological processes that have erased almost all of Earth's ancient rock. A message in stone from the very beginning of the solar system, sitting on a shelf, waiting for someone to understand its story. Tonight, we go to where that rock came from. We go to the asteroid belt. And within the asteroid belt, we visit two worlds that could not be more different from each other, despite forming in the same neighborhood of the early solar system, Ceres, a round, icy, geologically active dwarf planet with bright white spots that puzzled scientists for years, and an interior that may contain liquid water right now, and Vesta, a battered, rocky, ancient world with a crater so enormous it would dwarf any impact feature in the inner solar system, a world with an iron core like a planet and a history of violence written in its craters and cliffs. Everything I am going to tell you is true. Every fact, every measurement, every discovery. The asteroid belt is real. Ceres and Vesta are real. The Dawn spacecraft that orbited both of them and sent back their stories is real. And by the time we are finished, you will understand this extraordinary region of the solar system in a way that most people never stop to consider. Take a long, slow breath in right now. Fill your lungs all the way. Hold it for just a moment and breathe out slow, letting your whole body settle and release with the exhale. Feel where you are resting. Feel the weight of your body, comfortable and still. Let your eyes stay closed and heavy. You are safe, you are warm, and we are going on a journey to a region of the solar system between Mars and Jupiter, to a belt of millions of rocky worlds that has fascinated astronomers since the very first ones were discovered more than 2 centuries ago. Let us begin with the question of what the asteroid belt actually is, because the popular image of the asteroid belt, formed by decades of science fiction films showing spacecraft navigating through a dense, chaotic cloud of tumbling boulders, is almost entirely wrong. The asteroid belt is the region of the solar system between the orbit of Mars and the orbit of Jupiter, from about 2.2 to 3.2 times the Earth-Sun distance. Within this region, an enormous number of rocky bodies orbit the Sun. The total number of asteroids in the belt, with a diameter larger than 1 kilometer, is estimated at somewhere between 1 and 2 million. There are many more smaller ones. And yet, despite these enormous numbers, the asteroid belt is almost inconceivably empty. The total mass of all the asteroids in the belt combined is only about 4% of the mass of the Moon. The total volume of the belt, the three-dimensional space within which all these objects orbit is so large that each asteroid is separated from its nearest neighbor by millions of kilometers on average. A spacecraft traveling through the asteroid belt, as several have done on their way to the outer solar system, is in almost no danger of collision. The Voyager and Pioneer spacecraft, the New Horizons probe, the Galileo and Ulysses missions all traveled through the asteroid belt without taking any precautions for asteroid avoidance. The chance of encountering an asteroid at random in that region of space is extraordinarily small. The asteroid belt, despite containing millions of objects, is vast enough that it is essentially empty from the perspective of any individual traveler. Where did all this material come from, and why is it in a belt rather than having accumulated into a planet? This question puzzled astronomers for a long time after the first asteroids were discovered in the early 1800s. The earliest hypothesis was that the asteroids are the remnants of a planet that once existed between Mars and Jupiter and was somehow destroyed. This idea has appeal, but is almost certainly wrong. The total mass of the asteroid belt is far too small to have ever formed a significant planet. Even if all the asteroid belt material that has been lost over the history of the solar system is accounted for, the original asteroid belt probably never contained more than a few percent of Earth's mass. You cannot make a planet of any note from that. The correct explanation involves Jupiter. When Jupiter formed, it formed quickly and grew large before most of the other rocky material in the solar system had time to come together into larger bodies. Jupiter's enormous gravity stirred the material in the region between its orbit and Mars's orbit, continuously exciting the orbits of the small rocky bodies there, making them more elliptical and more inclined, causing them to collide with each other at higher velocities than would be needed for gentle accretion into larger bodies. When two asteroids collide at low velocity, they can stick together and grow. When they collide at high velocity, they shatter each other. Jupiter's gravity kept the collision velocities in the asteroid belt high enough to prevent the material from ever coming together. The asteroid belt is what it is because Jupiter would not allow it to be a planet. Over the 4.5 billion years since this stirring began, Jupiter has also ejected enormous amounts of material from the belt outright. Gravitational resonances with Jupiter, specific orbital periods that are simple fractions of Jupiter's own orbital period, cause asteroids in those orbits to receive regular gravitational tugs from Jupiter at the same point in every orbit. These tugs reinforce each other over time and eventually destabilize the orbit, sending the asteroid on a new trajectory that may carry it into the inner solar system, into a collision with Jupiter itself, or out of the solar system entirely. The gaps in the distribution of asteroid orbital periods at these resonance locations are called the Kirkwood gaps, after the American astronomer Daniel Kirkwood, who identified them in the 1860s. They are clearly visible when you plot the distribution of asteroid orbital periods. Certain specific periods are almost completely empty, swept clean by Jupiter's resonant gravitational action. The asteroids that have been ejected from the belt over billions of years have not simply disappeared. They ended up somewhere. Many became the near-Earth asteroids, objects whose orbits now cross or approach Earth's orbit. Some of these have struck Earth in the past. The impactor that contributed to the mass extinction that killed the non-avian dinosaurs 66 million years ago was almost certainly an asteroid from the main belt. Ejected into a resonance orbit by a gradual drift in its orbital period caused by the Yarkovsky effect, a tiny thermal force that slowly changes the orbit of small rocky bodies in sunlight. Others became the meteorites that fall to Earth, like the piece of Vesta with which we began. The asteroid belt is the reservoir from which the inner solar system has been periodically bombarded throughout its history. Asteroids come in several distinct types based on their composition. The most common are the C-type or carbonaceous asteroids. These are dark, primitive bodies with a composition similar to certain types of meteorites called carbonaceous chondrites. They contain the original material of the early solar system, including carbon compounds and water-bearing minerals, relatively unmodified since the solar system formed. They populate the outer regions of the main belt, where temperatures are lower and volatile compounds have been better preserved. C-type asteroids are scientifically precious because they are time capsules, preserving a record of the chemistry of the early solar system that has been erased from all the inner planets by billions of years of geological activity. The S-type or silicate asteroids are brighter than the carbonaceous ones. They are made primarily of silicate minerals and metal, similar to the rocks that make up Earth's mantle. They are common in the inner regions of the asteroid belt. Many of the meteorites that fall to Earth come from S-type asteroids. The M-type or metallic asteroids are thought to be the exposed cores of bodies that were once large enough to differentiate, to separate into a metallic core and a rocky mantle before being shattered by impacts. They are made primarily of iron and nickel, similar to the metallic cores of the terrestrial planets. The largest known M-type asteroid, Psyche, is the target of a NASA mission that launched in 2023 and is on its way to investigate this metal world in detail. Understanding Psyche will help scientists understand the nature of planetary cores, since we will never be able to directly access Earth's own iron core. Let your breathing settle deeper now. The asteroid belt is a crowded but vast and mostly empty place, and tonight we are visiting its two most remarkable inhabitants. Let us go first to Ceres, the largest object in the asteroid belt, the only dwarf planet in the inner solar system, a world that has surprised scientists repeatedly and continues to reveal new aspects of itself with each new analysis of spacecraft data. Ceres was the first asteroid ever discovered. On January 1st, 1801, the Italian astronomer Giuseppe Piazzi was working at the Palermo Observatory in Sicily, cataloging stars, when he noticed a faint object that moved against the background stars over successive nights. He tracked it for several weeks before illness prevented him from continuing. The mathematician Carl Friedrich Gauss developed a new mathematical method to determine the orbit of a celestial body from only a few observations, applied it to Piazzi's data, and predicted where the object would be found after it had moved too close to the sun to observe. Other astronomers pointed their telescopes to the predicted position and found the object exactly where Gauss said it would be. It was named Ceres, after the Roman goddess of grain and agriculture, the patron goddess of Sicily. For 50 years, Ceres was classified as a planet. Then, as more and more similar small bodies were discovered in the same region of the solar system, they were reclassified as a new category of object, the asteroids. Ceres, despite being by far the largest, was demoted to asteroid. Then in 2006, when the International Astronomical Union developed new definitions for solar system bodies and reclassified Pluto as a dwarf planet, Ceres was simultaneously elevated to dwarf planet status, recognizing its unique character. Ceres is now both an asteroid and a dwarf planet, the only object in the inner solar system to hold both classifications simultaneously. Ceres is significantly larger than any other asteroid. Its diameter is about 945 kilometers, making it roughly spherical, pulled into this shape by its own gravity. It is large enough that its gravity is sufficient to collapse it into a roughly round form, which is one of the criteria for dwarf planet classification. The next largest object in the asteroid belt, Vesta, has a mean diameter of about 525 kilometers, significantly smaller than Ceres. After Vesta, the sizes drop off rapidly. There is no third asteroid that approaches the size of the two largest. Ceres orbits the Sun at an average distance of about 77 times the Earth-Sun distance in the outer middle region of the asteroid belt. It takes about 4.6 Earth years to complete one orbit. Its rotation period is about 9.07 hours. It is tidally locked to nothing, spinning freely with a moderate obliquity, experiencing seasons as it orbits the Sun. What makes Ceres extraordinary is its composition and its internal structure. Ceres is not simply a rock. It contains a significant fraction of water. Somewhere between 20 and 25% of its mass may be water ice. This makes it one of the largest repositories of water in the inner solar system after Earth. The water ice is not on the surface in a form that is easily visible from orbit. It is within the interior, perhaps forming a thick icy mantle surrounding a rocky core, or mixed into the rock in a complex layered structure. Some of it may still be liquid, maintained by the remnant heat of Ceres's formation, which has not yet entirely escaped into space. The possibility of liquid water in the interior of Ceres is one of the most scientifically interesting aspects of this small world. The Dawn spacecraft, which we will discuss in detail shortly, observed bright spots on the surface of Ceres that were visible even from early approach images. As Dawn moved closer and its camera resolution improved, the bright spots resolved into clusters of highly reflective material inside craters. The most spectacular are an Ocator crater, a 92-kilometer wide impact crater in the northern hemisphere of Ceres. The floor of Ocator crater contains two distinct bright areas. The central one, called Cerealia Facula, is the brighter of the two and covers an area of several kilometers. The other, called Venalia Faculae, is a more diffuse collection of bright patches on the crater floor offset from the center. The bright material in Ocator crater is made primarily of sodium carbonate, a salt. It was deposited there by a process called cryovolcanism, the volcanic eruption of water and other volatile compounds instead of silicate lava. After the impact that created Ocator crater, the heat of the impact melted material in Ceres's subsurface, releasing briny water that welled up toward the surface through fractures. As this brine reached the low-pressure environment near the surface, the water in it sublimated and escaped, leaving behind the salt deposits that are now visible as the bright spots. The process is thought to have continued for millions of years after the impact and may still be ongoing at a low level today. Dawn detected water vapor around Ceres, specifically in the region of the bright spots, consistent with the sublimation of water from the surface. It also detected organic molecules on the surface of Ceres in the region of the Ernetet crater, in concentrations higher than would be expected from purely geological processes. Organic molecules, complex carbon-containing compounds, are thought to be necessary precursors to life. Their presence on Ceres, combined with the presence of water, makes Ceres a scientifically interesting target in the search for conditions that could support or have supported simple chemistry of the kind associated with biology. The Dawn mission also detected haze inside Okator crater, a thin, transient haze that appears and disappears on timescales of hours. This haze is thought to be caused by the sublimation of ice or volatile compounds near the bright spots, producing a very thin local atmosphere inside the crater that condenses and disappears as the surface temperature changes through the Cererian day. It is the closest thing to a regular dynamic atmospheric phenomenon yet observed on any asteroid or dwarf planet in the inner solar system. The Dawn spacecraft used its gamma ray and neutron spectrometer to detect the presence of hydrogen in the soil of Ceres near the poles. This hydrogen is most likely present as water ice in the shallow subsurface of the polar regions, where permanently shadowed areas never receive direct sunlight, and temperatures are cold enough for water ice to be stable over long geological time periods. This polar ice may have been deposited over billions of years by a variety of processes, including impacts by water-bearing asteroids and comets and the migration of water vapor across the surface. Now let us leave Ceres and travel to Vesta. If Ceres is surprising because of what it is, Vesta is surprising because of what it is not. It is not what you would expect from an asteroid. Vesta was discovered on March 29, 1807, by the German astronomer Heinrich Wilhelm Olbers. It was the fourth asteroid ever discovered. Its name comes from the Roman goddess of the hearth and home. Vesta is the brightest asteroid in the sky, occasionally bright enough to be seen with the naked eye from Earth under ideal dark sky conditions. This brightness initially suggested to astronomers that it might have a surface very different from the dark, carbonaceous asteroids. They were right, but not in the way they anticipated. Vesta has a mean diameter of about 525 kilometers, but it is not spherical. It is somewhat elongated, with a shape that reflects a complex geological history rather than simple gravitational compression into a smooth ball. Its surface is the most reflective of any large asteroid in the belt, made of silicate minerals that reflect sunlight efficiently, and it has a structure that sets it fundamentally apart from almost all other known asteroids. Vesta is differentiated. This is a geological term, meaning that its interior has separated into distinct layers based on density, in the same way Earth, Mars, and the other terrestrial planets are differentiated. Vesta has an iron-nickel core, a rocky mantle, and a rocky crust. It is, in a geological sense, a planet trapped in a small body. It formed large enough and melted thoroughly enough early in the solar system's history that the dense iron sank to its center and the lighter rock floated to the surface. It was on its way to becoming a full-sized rocky planet when Jupiter's gravitational interference prevented it from growing further. How do we know Vesta has an iron core? The answer involves the meteorites in our museum collections. For more than a century, scientists have studied a group of meteorites called the Head Group, named for the three main types within it: Howardites, Eucrites, and Diogenites. These meteorites are volcanic rocks, igneous rocks, crystallized from molten magma. They come from a differentiated body, one that was large enough to melt and have magma flowing on its surface. Analysis of their compositions suggested they all came from the same parent body, and the characteristics of that parent body, its size, composition, and geological history as inferred from the meteorites, matched Vesta remarkably well. The head meteorites are fragments of Vesta, knocked off the surface by impacts and sent drifting through the solar system until Earth's gravity captured them. There are hundreds of head meteorites in collections around the world. They are pieces of another world that we can hold in our hands and study in laboratories. Through them, scientists had a detailed picture of Vesta's geological character even before any spacecraft visited it. The Dawn mission's subsequent observations confirmed that the head meteorites do indeed come from Vesta, verifying the match between the meteorite compositions and the surface composition of the asteroid as measured from orbit. The surface of Vesta is ancient and heavily cratered. Unlike Ceres, which shows evidence of relatively recent geological activity through its bright spots and hazes, Vesta is a geologically dead world, its interior cooled and solidified long ago. Its surface has been accumulating impact craters for billions of years without the resurfacing processes that would reset the clock. The oldest terrains on Vesta are among the most ancient surfaces in the solar system, dating to the very earliest period after the solar system formed. The southern hemisphere of Vesta is dominated by two enormous impact basins that together define the character of this world. The older and smaller of the two is called Venonea, about 400 kilometers in diameter. Superimposed on it is the younger and far larger Rhea Silvia basin, about 505 kilometers in diameter. This is larger than the diameter of Vesta itself, which at 525 kilometers mean diameter means the impact that created Rhea Silvia must have come very close to destroying Vesta entirely. The impact excavated a depression almost 19 kilometers deep and threw an enormous amount of material off the surface of Vesta. At the center of the Rhea Silvia basin stands a mountain that is one of the most remarkable topographic features in the solar system. The central peak of Rhea Silvia rises to a height of about 22 kilometers above the floor of the basin. This is the tallest mountain in the solar system relative to the size of the body it stands on, and it rivals Olympus Mons on Mars in absolute height. Though it rises from a depression rather than a plain, it formed as the crust rebounded after the enormous impact, the same process that creates central peaks in lunar craters, but operating at a scale that produced a mountain taller than anything on Earth. The material blasted off Vesta by the Rhea Silvia impact went in all directions. Some of it fell back onto Vesta, creating a scattering of secondary craters across the surface. Some of it achieved escape velocity and drifted away from Vesta into nearby orbits in the asteroid belt. This escaped material makes up the Vesta family of asteroids, a group of smaller bodies with orbital characteristics and compositions similar to Vesta that are clearly fragments from this ancient impact event, and some of the material drifted into orbital resonances with Jupiter, was perturbed into new orbits, and eventually fell into the inner solar system, landing on Earth as the head meteorites. The Rhea Silvia impact also had a global effect on Vesta's surface. The shockwave from the impact traveled through Vesta and produced a system of long, parallel grooves and troughs that gird the equatorial region of the asteroid. These features, called the Divalia Fossae, are long linear depressions extending thousands of kilometers around the equator of Vesta. They look like the seams of a cracked egg, radiating from the center of the impact and tracing paths around the globe. Similar features, called the Saturnalia Fossae, are associated with the older Venonea impact. Together, these two sets of tectonic grooves give Vesta's equatorial region a distinctive banded appearance that is immediately visible in spacecraft images. The Dawn spacecraft. Now let us talk about the mission that visited both Vesta and Ceres and transformed our understanding of both worlds. Dawn was a NASA Discovery mission designed to investigate the two most massive bodies in the asteroid belt. It launched on September 27, 2007, on a Delta II rocket from Cape Canaveral. The spacecraft was unusual in its propulsion system. Rather than using conventional chemical rocket engines, Dawn was powered by ion propulsion, a technology that uses electric fields to accelerate ions of xenon gas to extremely high velocities, generating thrust. Ion propulsion provides very small thrust, far less than a conventional rocket, but it can continue operating for years, gradually building up to speeds that would be unachievable with chemical propulsion for a spacecraft of Dawn's mass. Dawn arrived at Vesta in July 2011, entered orbit, and spent about 14 months studying the asteroid from various altitudes. It then departed Vesta in September 2012, used ion propulsion to travel across the asteroid belt, and arrived at Ceres in March 2015, becoming the first spacecraft in history to orbit two extraterrestrial bodies. After more than 3 years at Ceres, Dawn's fuel supply for attitude control was exhausted in October 2018, ending the mission. The spacecraft remains in a stable orbit around Ceres, where it will continue to circle for at least decades before eventually impacting the surface. The measurements Dawn made at both Vesta and Ceres are still being analyzed, still yielding new discoveries. The gravity mapping it performed at both bodies revealed their internal structure with unprecedented detail. The compositional mapping, using its visible and infrared spectrometer, identified the minerals present on their surfaces. The crater counting established the geological timescales of different terrain types, and the camera images created the most detailed maps of both worlds that will likely remain the best available for many years. Before we drift towards sleep, let us think about the asteroid belt in a broader context. In a way, it is the solar system's scrap heap, the material that never quite made it into a planet. But this scrap heap contains information that cannot be found anywhere else. The asteroids, particularly the primitive carbonaceous C-type asteroids, preserve a record of the composition of the early solar system that has been erased from all the planets by billions of years of geological processing. They are the raw material from which the planets were made, still sitting there, preserved in the cold of the outer inner solar system, waiting to be read. Let us look more closely at some of the individual asteroids that have been studied by spacecraft before we think about the broader significance of the belt. The asteroid Eros was the first near-Earth asteroid ever discovered, found in 1898. It is an elongated, irregular body about 34 kilometers long and 11 kilometers wide, shaped somewhat like a lumpy potato or a kidney bean. The Near-Shoemaker spacecraft entered orbit around Eros in February 2000 and became the first spacecraft to orbit an asteroid. It spent about a year in orbit, mapping the surface in detail before landing on the surface in February 2001, the first successful landing on an asteroid in history. Eros is an S-type asteroid made of silicate rock, similar to the rock of Earth's mantle. The near mission revealed a surface blanketed in boulders and craters with a regolith layer that has been thoroughly processed by billions of years of micrometeorite impacts. Eros's surface contains a prominent saddle-shaped depression called Hemeros, which may be an old, partially buried impact crater, and a large crater called Psyche that dominates one end of the body. The asteroid Eta was photographed by the Galileo spacecraft in August 1993 as it flew through the asteroid belt on its way to Jupiter. The images were extraordinary for two reasons. First, they showed an S-type asteroid with a complex, cratered surface in detail never seen before. Second, they revealed that Eta has a small moon orbiting it. The moonlet, named Dactyl, is only about 6 kilometers across and orbits Ida at a distance of about 90 kilometers. Dactyl was the first confirmed moon of an asteroid ever discovered. We now know that many asteroids have moons, and some even have two. The discovery of Dactyl opened an entirely new chapter in the study of small bodies in the solar system. The Japanese asteroid Itokawa was visited by Japan's Hayabusa spacecraft, which arrived in 2005 and spent several months studying this small, peanut-shaped S-type asteroid about 535 meters long. Itokawa appears to be a rubble pile, an object held together not by solid rock, but by the loose gravitational attraction of a collection of rocky fragments with very little internal cohesion. The surface has almost no fine regolith in many areas, because the very weak gravity of this small body means that loose material tends to drift away over time. Hayabusa successfully collected tiny samples of surface material from Itokawa, enduring numerous technical problems that required the spacecraft team to improvise solutions over months of difficult operations. The samples were returned to Earth in 2010 and have been studied extensively. They confirmed the S-type classification and revealed details about the history of Itokawa that could not have been determined by remote observation. The asteroid Bennu, visited by NASA's OSIRIS-RX mission, is a different kind of object entirely. Bennu is a C-type asteroid, carbonaceous and dark, about 490 meters across. OSIRIS-RX arrived at Bennu in December 2018 and spent nearly 2 years in orbit, mapping the surface in extraordinary detail. Bennu turned out to be another rubble pile, and its surface was covered in boulders of all sizes, far more boulders than scientists had expected, based on observations from Earth. The surface material on Bennu was also surprisingly fluffy and loosely consolidated. When the spacecraft descended to collect samples in October 2020, the sample collection head penetrated about 50 centimeters into the surface before the thrusters fired to pull the spacecraft back up. The sample container was so full of material that the lid could not close completely, and some material leaked back into space before the container was sealed. The samples that did make it back to Earth in September 2023 were extraordinarily rich, containing more than 120 grams of material, including water-bearing minerals and organic compounds. The organic compounds in the Bennu samples include amino acids and other molecules relevant to the chemistry of life, confirming and extending the findings from the Ryugu samples returned by Hayabusa 2. The Yarkovsky effect, mentioned earlier in connection with how asteroids drift into orbital resonances, deserves its own explanation, because it is one of the most elegant examples of a very subtle physical effect having major consequences over long timescales. When sunlight falls on an asteroid, it heats the surface. The heated surface later radiates this energy away as infrared radiation. But because the asteroid is rotating, the radiation is not emitted symmetrically. The side that was in the sun during the day has rotated around to the night side before it is cooled fully, so it radiates more heat in the direction of the asteroid's motion than opposite to it, or vice versa, depending on the direction of rotation. This asymmetric radiation of energy creates a tiny but continuous force on the asteroid, very gradually changing its orbital speed and thus its orbital radius. Over millions of years, this tiny force can move an asteroid significantly from its original orbit, potentially drifting it into a resonance with Jupiter that then ejects it from the belt entirely. The Yarkovsky effect is why small asteroids and the meteorites that come from them represent a different orbital population from the larger asteroids that are too massive to be significantly moved by this thermal radiation force. Meteorites deserve their own section in this story because they are the direct physical connection between the asteroid belt and Earth. Every meteorite that has ever been found on Earth is a fragment of the asteroid belt, or in some cases of Mars or the Moon. Meteorites fall to Earth continuously, with an estimated total of several thousand kilograms of meteoric material reaching Earth's surface every day, though most of this is in the form of tiny dust particles. Larger meteorites fall less frequently. Several hundred meteorites of at least kilogram size reach the surface every year, though most fall into the ocean or in remote areas and are never recovered. Scientists classify meteorites into broad categories based on their composition and structure. Stony meteorites are the most common and include the chondrites, the most primitive type, which have not been significantly modified since the solar system formed. Chondrites contain tiny spherical structures called chondrules, droplets of once molten silicate that solidified quickly in the early solar nebula before being incorporated into the growing asteroid. The presence of chondrules in a meteorite is evidence that the parent body was never large enough to melt and destroy these structures. The carbonaceous chondrites are a subset of the chondrites that contain significant amounts of carbon compounds and water-bearing minerals preserved from the very earliest history of the solar system. The stony iron meteorites are a smaller category containing both silicate minerals and metallic iron in roughly equal amounts. They are thought to come from the boundary between the rocky mantle and the iron core of differentiated asteroids excavated by impacts. They have a distinctive, beautiful appearance when cut and polished, with geometric patterns of silicate crystals embedded in a metallic matrix. The most visually spectacular type, the pallasites, show olivine crystals of yellowish-green color embedded in a shining metallic iron-nickel matrix. They are among the most beautiful natural objects in existence. The iron meteorites are fragments of the cores of differentiated asteroids, essentially pieces of ancient planetary cores that were blasted out by enormous impacts. When cut and etched with acid, iron meteorites often display a distinctive pattern of interlocking crystal structures called Widmanstätten patterns, formed by the extremely slow cooling of iron-nickel alloy over millions of years in the interior of an asteroid. The crystal sizes in these patterns reveal the cooling rate, typically just a few degrees Celsius per million years. The cooling rate tells scientists the depth within the parent asteroid at which the iron crystallized, allowing them to infer the size and structure of the parent body. Iron meteorites are time capsules recording the thermal history of planetary cores that no longer exist as intact bodies. The connection between specific meteorite types and specific asteroids is one of the great achievements of planetary science over the past half-century. For many years, scientists could only hypothesize about the origins of specific meteorite types. With spacecraft missions to asteroids, the hypotheses could be tested directly. The head meteorites from Vesta are the best confirmed example, but the matches between other meteorite types and other asteroid spectral types have also been confirmed and refined through a combination of laboratory analysis and spacecraft observation. Let us return briefly to Ceres and spend a moment thinking about its geological evolution over the history of the solar system. Ceres formed in the outer part of the asteroid belt, where temperatures were cold enough for water ice to be incorporated into the growing body alongside the rocky minerals. As Ceres grew, its interior began to heat from the decay of radioactive elements incorporated at formation. This heat melted the ice in the interior, allowing liquid water to interact with the rocky minerals and producing the hydrated minerals that are now detected spectroscopically on the surface. If the interior heated enough, the rocky core may have separated from the icy mantle, producing a differentiated structure, even though Ceres is small enough that this differentiation may be incomplete. Over the following billions of years, Ceres cooled as the radioactive elements decayed away and their heat production diminished. The outer layers froze. The interior may have retained some liquid water, insulated by the overlying ice and rock. Impacts continued to excavate and expose material from different depths, mixing the surface and creating the complex terrain of craters and ridges and plains that Dawn mapped. The bright spots, the product of cryovolcanic activity driven by impact-generated heat, are among the youngest features on the surface. They tell us that even now, after 5 billion years, Ceres is not entirely geologically finished. The comparison between Ceres and Vesta is one of the most informative in planetary science, because the two objects formed in the same general region of the solar system at the same time from similar starting materials and yet evolved in completely different directions. Vesta heated rapidly and thoroughly, driven by the decay of a short-lived radioactive element called aluminum-26 that was abundant in the early solar system but decays away within a few million years. This rapid heating caused Vesta to differentiate completely, forming an iron core, a rocky mantle, and a basaltic crust. By the time the radioactive heating faded, Vesta was fully differentiated, and its geological evolution was essentially complete. It has been slowly accumulating impact craters ever since. Ceres heated more slowly, perhaps because it formed slightly later or in a region with slightly less aluminum-26. It never fully differentiated. Its interior remained a mixture of rock and ice rather than separating cleanly into distinct layers. The ice preserved it from some of the heating that fully differentiated Vesta, because melting ice absorbs heat. The result is two worlds that tell complementary stories about the range of geological evolution possible among bodies that formed in the early solar system. The study of these two worlds, combined with the study of meteorites from differentiated and undifferentiated parent bodies, has given planetary scientists a detailed picture of how rocky bodies evolve during the first few tens of millions of years of the solar system, a period that is otherwise inaccessible because all the planets that formed in the inner solar system have been thoroughly geologically processed since then. Ceres and Vesta are windows into an era that cannot be studied any other way. Recent missions to asteroids have brought this material directly to Earth. Japan's Hayabusa mission returned samples from the asteroid Itokawa in 2010. The Hayabusa 2 mission returned samples from the asteroid Ryugu in 2020. NASA's OSIRIS-RX mission returned samples from the asteroid Bennu in 2023. These tiny samples, just grams of material collected from asteroid surfaces, have provided new information about the composition of the early solar system and the distribution of organic compounds in it. The Ryugu samples, in particular, contained a rich variety of organic molecules, including amino acids, the building blocks of proteins on Earth. These organic compounds were present in the asteroid before any life existed on Earth, demonstrating that the chemical precursors of life were distributed throughout the early solar system. The asteroids also represent potential resources for the future. The metallic M-type asteroids contain enormous quantities of iron, nickel, cobalt, and platinum group metals. A single large metallic asteroid could contain more of these metals than humanity has mined in all of recorded history. The carbonaceous asteroids contain water, carbon, and other volatile compounds that would be essential for any extended human activity in space. Asteroid mining has moved from pure science fiction to active commercial research over the past decade. Several companies have been formed with the intention of eventually mining asteroid resources. The technical challenges remain formidable, and the economic viability is still unproven, but the resource potential is real. The question of asteroids and Earth's future is also relevant. Near-Earth asteroids, those whose orbits bring them close to or across Earth's orbit, represent a potential hazard. Several impacts have occurred in recorded history, including the Tunguska event in 1908, when a small asteroid or comet fragment exploded in the atmosphere over Siberia and flattened roughly 2,000 square kilometers of forest. The Chelyabinsk event in 2013 sent a roughly 20-meter asteroid exploding in the atmosphere over Russia. injuring more than 1,000 people from the shockwave and broken glass. And the geological record contains the evidence of much larger impacts that had catastrophic consequences for life on Earth. In 2022, NASA demonstrated for the first time that a spacecraft can deliberately change the orbit of an asteroid. The DART mission, which stands for Double Asteroid Redirection Test, crashed a spacecraft into the small moonlet Dimorphos, which orbits the larger asteroid Didymos. The impact successfully changed the orbital period of Dimorphos by more than 30 minutes, far more than the minimum required to demonstrate the technology. Planetary defense, the science and technology of deflecting potentially hazardous asteroids, has moved from theoretical to proven in the course of a single decade. The tools to protect Earth from the kind of asteroid impact that ended the dinosaurs are being developed, tested, and refined. The asteroid belt, in all of its aspects, is one of the most scientifically rich regions of the solar system. Its millions of objects preserve the history of the solar system's formation. Its two largest members, Ceres and Vesta, are each extraordinary worlds that push the boundaries of our understanding of planetary formation and geological evolution. Its samples, arriving on Earth as meteorites and now as deliberately collected material from spacecraft missions, are transforming our understanding of the chemistry of the early solar system, and its resources and hazards are shaping the future of space exploration and planetary defense. Let us pause for a moment and consider what it means for Earth that the asteroid belt exists where it does. The presence of Jupiter, the planet that prevented the asteroid belt from becoming a planet, has had consequences that extend far beyond the asteroid belt itself. Jupiter's gravity has swept many potentially dangerous asteroids and comets out of the inner solar system over billions of years. Some scientists believe that without Jupiter, Earth would have been bombarded much more frequently by large impactors, potentially making the emergence of complex life more difficult or impossible. Jupiter, by capturing much of the incoming debris, has played the role of a gravitational shield, protecting the inner solar system from the most extreme impacts. This idea is sometimes called the Jupiter shield hypothesis. At the same time, Jupiter's gravitational influence on the asteroid belt has been sending a steady trickle of material into the inner solar system throughout Earth's history. Some of this material has been catastrophic, like the impactor that contributed to the mass extinction at the end of the Cretaceous period, but some of it has been beneficial. The early bombardment of Earth by water-bearing asteroids and comets may have been partly or largely responsible for delivering the water that fills Earth's oceans. The C-type carbonaceous asteroids, with their content of water-bearing minerals and organic compounds, may have delivered the raw materials for life to the early Earth. The asteroid belt, in this view, is not just a hazard. It is a supplier. It delivered the water we drink and possibly the organic molecules from which life arose before becoming the rocky reservoir from which occasional impacts still emerge. The history of asteroid discovery reflects the history of observational astronomy over the past 2 centuries. After Ceres in 1801, Pallas was discovered in 1802, Juno in 1804, and Vesta in 1807. These 4 were for decades the only known members of the asteroid belt. Then, in 1845, a 5th asteroid was discovered, and then more rapidly thereafter. By 1890, several hundred were known. By 1950, several thousand. Today, the count of known asteroids exceeds 1 million, and new ones are being discovered by automated sky survey programs at a rate of thousands per month. The Minor Planet Center, maintained by the International Astronomical Union, catalogs all known small solar system bodies. It is a remarkable document of human curiosity, a list that began with one object named Ceres and now contains over 1 million entries. The survey programs that find new asteroids serve a dual purpose. They advance science by expanding our understanding of the distribution and characteristics of small bodies in the solar system, and they serve planetary defense because finding and cataloging near-Earth asteroids tells us what is out there and whether any of it poses a future threat to Earth. The Catalina Sky Survey, the Pan-STARRS Survey, the Atlas Survey, and others continuously scan the sky, automatically detecting moving objects and determining their orbits. Any object whose orbit brings it close to Earth is flagged for follow-up observation. The probability of any given known asteroid striking Earth over the next century can be calculated with remarkable precision from its orbital parameters. For the vast majority of known near-Earth asteroids, the probability is essentially zero. For a small number, it is not zero, but is very small. And for one or two, the probability has been calculated with enough uncertainty that they remain on watch lists for further observation. The state of our knowledge of the asteroid belt today is extraordinary compared to what was known even 50 years ago. In the 1970s, asteroids were points of light in telescopes, their sizes and compositions estimated indirectly from their brightness and color. Now we have detailed maps of their surfaces, samples of their soil, measurements of their gravity fields and internal structures, and direct chemical analysis of their atmospheric emissions in the case of Ceres. The next generations of sky surveys, including the Vera C. Rubin Observatory, currently under construction in Chile, will catalog tens of millions of new asteroids over the course of their operating lifetimes, extending our inventory of the solar system's small bodies to previously unimaginable depth. The story of the asteroid belt is, in a very real sense, the story of how the solar system failed to make a planet in one specific region, and how that failure preserved a record of the solar system's earliest chemistry that would otherwise have been lost. The failure created Ceres and Vesta and millions of other fascinating small worlds, each one a different window into the first moments of the solar system. It created the meteorites that we find on Earth. It created the material that may have brought water and organic chemistry to the early Earth, and it created a region of space that humanity is now beginning to visit, study, and someday perhaps utilize. You are very close to sleep now. Let everything settle gently. Let the asteroid belt drift peacefully in the background of your mind. The millions of rocky objects orbiting quietly in the space between Mars and Jupiter. Ceres, small and round and icy, with its bright spots glowing in the permanent dark of space, and its subsurface perhaps still holding liquid water after 4.5 billion years. Vesta, battered and ancient, wearing the enormous crater of Rhea Silvia like a wound from the early solar system, its mountain towering 22 kilometers from the crater floor, its grooves circling the equator, its iron core a reminder of the planet it never quite became. The piece of Vesta in the Houston Museum is still there, It came from the collision that made Rhea Silvia. It traveled billions of kilometers across the solar system. It fell through the atmosphere of Earth as a fireball, visible for hundreds of kilometers, and survived the descent to the surface. And now it sits in a case, still and quiet, carrying in its minerals and crystal structures a record of events that happened in the first few million years of the solar system's existence. Before Earth had formed, before the moon existed, before anything alive had yet drawn a breath on any planet anywhere. The asteroid belt will still be there tomorrow. Ceres will still be slowly brightening and dimming as the bright spots of Vocator rotate into and out of view. Vesta will still be turning, showing its enormous southern basin to space, and then turning it away. Dawn will still be orbiting Ceres silently, its instruments dark, its mission complete, its data back on Earth being studied by scientists who are still finding new things in it years after the spacecraft stopped transmitting. The solar system is ancient and extraordinary and still being understood, and you are resting comfortably in it. On the small blue world that formed from the same disk of material as Ceres and Vesta and all the millions of asteroids, the world that succeeded in becoming a planet where they did not, the world where the material of the asteroid belt eventually produced, through billions of years of evolution, creatures who could build spacecraft to go and visit it. Sleep now. Let everything be quiet and still. Good night.